familiar with more modern motivations, especially in the big data era. And some of these are the terms of data poisoning and adversarial attacks. Essentially, we have data sets and our machine learning models are being deployed in situations where we don't really have full control over what's going on. For example, maybe we gather a large data set and we don't really know the source of all this data, we don't trust it all, or maybe we're deploying a machine learning system in a situation where we don't know who's going to be interacting with it and they can do nasty things. And it turns out that current machine learning systems are surprisingly brittle. For example, here's a picture which many of you I'm sure have seen before. So let me just sort of explain what this is saying. So on the left here, you'll see on the left, there's this picture of a panda, which any of you will say is a panda. And in fact, a state-of-the-art image classifier will also say this is a panda with 57.7% confidence. I'm sure we can do better now with modern, this is from a few years ago. So this is a panda, we all agree on that. But imagine you add an imperceptible amount of noise. This sort of like very weird looking noise, and you sort of scale this down to an imperceptible level, then you get something that looks like the picture on the right. We, again, will all agree that this is a panda, but in fact, a machine learning system might say that this is a gibbon with 99.3% confidence. So something is wrong here. This is clearly something undesirable. This is just one example of a failure of, in terms of the level of robustness of modern machine learning. Something a bit closer to the setting which we'll consider here in today's talk is the following. So this is from a paper by Gu et al. And you can see here, what they did was they essentially did a data poisoning attack on a sign database. For example, they trained a machine learning model, an image classifier on a set of stop signs, speed limit signs, stuff like that. And you can see that they manually changed some of these images to have, a little few pixels, which is a yellow square, a picture of a bomb, a picture of a flower. And then when an image classifier was trained on this sort of poison data set. This is what's known as a backdoor attack. So they sort of put a backdoor here. And then in the real world, they went and put a physical sticker. This is a stop sign that's near NYU. They put a physical sticker on the stop sign, and you can see their image classifier now. So there's a speed limit sign with 95% confidence. So this is, again, a failure of robustness. And let me show you one of my favorite ones, just as one last one. I really love this one, and I want to show it to you. So this is what they call an adversarial turtle. So here's a regular turtle, regular 3D printed turtle, and here's Google's Inception v3 classifier, which, it'll classify the turtle, a terrapin type of turtle, which is great. But here's another turtle, and you can see this is classified as a rifle. And in fact, even if you rotate it from all angles, it's classified as a rifle. So this is a very specially crafted 3D printed turtle with a specifically designed to fool this image classifier. So this is all fun and games, it thinks a turtle is a rifle, but imagine you were at a security checkpoint and it was thinking a rifle it thought a turtle was a rifle, but what if we thought a rifle was a turtle? That's not quite as, not good, let's say. Yeah, so the overarching question here that we're trying to address is, can we develop algorithms which are provably robust to this worst case noise? And today I'll focus on, I'm a theorist by training, so and at my heart. So I'll start with some of the more simple settings. We'll look at some very fundamental settings and show what we can do there. And then we'll work our way up and go a little bit more complex into some fundamental supervised learning tasks. And of course, if there's any questions, feel free to ask. I'm not sure how to bring up the chat window actually, but Raphael, I'm sure can let me know if there's any questions, or also just unmute yourself, and that's fine too. Okay, so I'm going to present this as a sort of journey, because it was a journey that started roughly in 2015 with our first paper with this cast of characters: Ilias Diakonikolas, Daniel Kane, Jerry Lee, Ankur Moitra, and Alistair Stewart, with a paper at Fox 2016 titled "Robust Estimators and High Dimensions Without the Computational Untractability." So let's start with the basics. Forget about robustness for now. Let's just do classical parameter estimation. Suppose we're given samples from an unknown distribution in some class, for example, a 1D Gaussian. Can we accurately estimate its parameters? And this is like stats 101 stuff. I was flashing this book earlier, which I arrived today, and I looked it up. Literally on page 3, they have some coverage on how to estimate a distribution from its parameters like this. It's very, very simple. You can just take the empirical, mean, and variance. And you take a bunch of samples, you average them, you'll get an estimate for the mean. You take a bunch of samples, you compute the empirical variance, and that'll give you an estimate for the variance. And if you take enough samples, which I won't go too much into what enough is, this estimates it. So this is very easy in the non-robust setting. We can just take samples, take the empirical moments. Not a problem at all. However, things get more complicated when we switch to the robust setting. Now let's define the model and try to see what I mean by the robust setting. Suppose we're given corrupted samples from a 1D Gaussian. So our setting is going to be something like the following. We imagine that there is some ideal model, which is truly, say, Gaussian. And then you have some corruptions. And then what you see is the observed model, which is a proxy for the ideal model. So you only get to see something, the ideal model you never get to observe directly. You only observe it through some corruption model. And the question is, in this setting, can we accurately estimate its parameters? So let's be a bit more precise as to what we mean by this middle part here, corruptions. What does it mean to corrupt a distribution? And we'll do the following type of setting. So the following will be our corruption model. We'll imagine that an adversary can move an epsilon fraction of the data set arbitrarily. So to illustrate this, imagine this is our data set. All these blue points are the clean samples. But then an adversary comes along and changes an epsilon fraction of the points however they like. So you can see the data set before, and now you can see these red points on the right are moved adversarially. So let me just illustrate. You can see points from the left over here are moved over to the right. So you can imagine that this will shift the empirical mean of our data set and stuff like that. So, right. This is the adversary model, and it's very important that we understand it. I usually like to pause for an awkwardly long time in real life talk, so let me pause for an even more awkwardly long time here because it's a bit slower to ask questions, because this is like kind of important, the adversary model.
What was the previous picture?
Which one? This goose?
Yeah.
It's our adversary. He's who we're trying to look out for. He's trying to ruin our day, you know.
I understand. Oh, okay. I thought that you were actually going to be using that picture.
No, this is just a one-off.
That's just a normal Waterloo experience.
Exactly, yeah. Don't worry, this guy won't be showing up again.
Well, they've got the whole campus now.
Exactly, they've taken over. Anyway, so yeah, the adversary model is that an adversary will move an epsilon fraction of the data set arbitrarily. All right, let's proceed. So the formal problem statement will be something like the following. We're given an epsilon corrupted set of samples from a Gaussian, where it's defined in this way. And the goal is to efficiently find parameters mu hat and sigma hat, that is proxies for the mean and variance, such that the L1 or total variation distance between the true distribution and the one with these proxy parameters is O of epsilon. The best possible error in this corruption model is literally epsilon. So we'll try to be competitive with this up to a multiplicative constant factor. That's our sort of gold standard, our goal. One more thing I'll mention, by the way, is that this corruption model is very related to some classical method settings in statistics. For example, some of you might be familiar with Huber's contamination model, and it's essentially, it's actually even harder than that. But yeah, so the goal is to estimate it up to L1 or total variation distance epsilon. And in this talk, we're not going to worry about sample complexity in the sense that everything will be okay. We're not going to pay a large amount for these robust methods, but I'll just sort of sweep these under the rug for the time being. We can chat about it more later. So this is the problem statement. And the immediate question you might ask is, do the empirical mean and variance work? And if you saw in the previous, a few slides ago, that the answer is pretty immediately no. And the reason is for the following reason. You can imagine that you have your data set, but the adversary moves a single point out very, very far to the right. You can imagine the further out you put it, the further the empirical mean will be shifted. So this will totally ruin the empirical mean and variance as well. However, so I just want to point out that even a single corrupted sample can arbitrarily corrupt estimates. Remember, we were trying to go for the case where we can handle a constant fraction of the data. So this seems to fail catastrophically. However, there are other statistics which are very well understood. For example, the median and interquartile range, which are examples of, these are examples of robust statistics based on order statistics of the data set.
But the prof is from CS.
There was a question or comment. Yeah,
I didn't have it muted for a second.
Oh, no worries. Okay, anyway, like I was saying, the median and interquartile range are effective statistics, which are robust in this setting. And you can use the median as a proxy for the mean. and the interquartile range as a proxy for the standard deviation. In case you're not familiar, I mean, the median I think should be familiar to many of you. It's essentially the 50th percentile of the data set, but the interquartile range is the difference between the 75th and the 25th percentile of the data set. So notice these are all based on quantiles or order statistics, which are known to be more robust. So in fact, you can say a very simple theorem about this setting. This is sort of a folklore result, not our result. But given an epsilon corrupted set of samples from a Gaussian, we're going to let mu hat be the median and sigma hat be the rescaled interquartile range of the data set. And in fact, this will give you exactly the thing we were going for. It'll give you an estimate of the distribution in L1 or total variation distance. So this was good. We had a problem in terms of robustness. We found some new statistics which worked great. We subbed them in and life is good. However, this is not the end of the story. This is great for one dimension, but the challenge is what if we are even in a multivariate setting, even 2 dimensions or say 100 dimensions? What do we do then? So it's not immediately clear. For example, we've talked about statistics like the median and interquartile range. It's not clear how to generalize these to higher dimensional settings. So let's see what the problem is in this setting. We're given an epsilon corrupted samples from, say, a d-dimensional Gaussian. And we want to efficiently find parameters mu hat and sigma hat, that is, again, proxies for the true mean and covariance, such that the total variation distance, or L1 distance, is O of epsilon. And in fact, today, we're going to make it even easier, just to keep things super simple. We're going to assume that the covariance is equal to the identity. We can handle the unknown covariance case, but this would get too technical for a talk like this, so we'll keep it nice and easy saying that the covariance is the identity. We can talk more offline about how to handle the unknown covariance case. But an equivalent way of phrasing this is that you want to find a proxy for the mean, which is close in L2 distance to the true mean, up to the same O of epsilon. Okay, so like I said, it's not clear how to generalize the approaches that I mentioned before, say median and interquartile range. What are some notions of a higher dimensional median? Maybe that seems like a nice place to start, right? Median worked in 1D, will it work in higher dimensions? Well, one approach is, say, the Tukey median, which might be familiar to many of the folks in the audience here who work on computational geometry. The great thing is that this is very accurate. It'll have this O of epsilon error guarantee. But the bad thing is that it's NP hard to compute. And you'll see this kind of if you look at the definition. It's very don't focus too much on this definition, but this is just to give you an impression of how this sounds like a hard problem. The Tukey depth of any point in space is the minimum number of data set points on one side of a hyperplane through a point. So you kind of consider rotating all hyperplanes, and you pick the one which is kind of it gets you out the quickest if you wanted to escape the data set. Don't worry too much about the definition. It just sounds kind of hard because you have to consider all possible directions. And then the Tukey median of a data set is the point with the maximum Tukey depth, which is not necessarily in the data set. So yeah.
So I just have a quick question.
Yep.
A constant approximation, would that suffice?
Let's see, a constant approximation.
Like something close to the median?
Yeah. I'm not sure if a constant approximation makes sense because it depends what you mean by constant or where the constant appears. But yeah, essentially an approximation would work, but this is also, it's hard to approximate, I think, on worst case data sets. Essentially what our main result will be, skipping ahead a bit, is that the fact, indirectly, it'll be saying that this is approximable on Gaussian data sets, for example. Yeah, good question. So yeah, this is one approach which statisticians have liked, the Tukey median, which is great in terms of the accuracy guarantee, but not great in terms of running time if you care about running it in more than, say, 5 dimensions or something, because it'll scale poorly. Another approach, which is perhaps more familiar to computer scientists, is...
just a quick question.
Yeah,
you're talking about high dimensions. What happens if you're in a fairly high dimension for these, but the intrinsic dimensionality is quite low?
Right, yeah, that's a good question. Say, some sort of sparsity, perhaps,
Yeah.
You can do things, it's non-trivial even in those settings, but in fact, my work today, which I'm going to be talking about, focuses on sort of the complete case, but there's been some other follow-up works by some of my collaborators and others, which also handles the sparse case. So that's good, yeah, because this is very important, especially in high dimensional can mean different things to different people. To me, it's going to mean something where the dependence is polynomially in the dimension, but other folks, it means that you want only a logarithmic dependent on the dimension. in which case you have to enforce a sparsity constraint.
But I mean, sorry, just to address a part of of Ian's problem is that if we assume like low dimensionality is not a robust notion, right? Like, so you'd have to somehow identify that the corrupted data set would be like low dimension, right? Because if I'm allowed to change epsilon, like a fraction of the points, I can go from a low dimensional representation to a really high dimensional representation, right? So
yeah, exactly. There's like some work on problems related to this and some hardness results like called like robust subspace recovery, for example. This is like a big field of study. So like if you can efficiently do that, then you can reduce to a lower dimensional space, but indeed like corruptions can sort of make the problem a lot more challenging. Cool. So like the Tukey median is a statistician's best friend. Computer scientist's best friend perhaps is the geometric median, which is, on the other hand, computer scientists, there's a result by Cohen et al., which shows that this is computable but in near linear time. On the other hand, the error guarantee is going to be much worse than before. We were aiming for an O of epsilon accuracy, but now we get an O of epsilon times square root d. So that is, we scale poorly in sort of moderate settings of moderate dimensionality. And if you're not familiar with it, I'll just flash the definition here. It's essentially the point that minimizes the sum of the L2 distances to the points in the data set, compared with the mean, which is the sum of the L2 distances squared. So we've seen two different definitions here, or two different possible approaches rather, and we've seen they both fail for different reasons. One is slow and one is inaccurate. And these sort of trends continue. There's other approaches, for example, naive pruning, which I won't describe, is fast but not accurate. There's a tournament approach, which is accurate but not fast. And we could keep going. There's a lot of different approaches. But the point is that, you know, all the known approaches before our work were either one of these two problems. They were either computationally intractable in high dimensions, that is NP hard or something like it, or they lose accuracy factors which depend polynomially on the dimension. Let me point out that, like, even in, say, 100 dimensions, this will be an extra factor of 10. You know, it gets even worse from there. 1,000,000 dimensions would be a factor of 1,000. So an equivalent way of stating that is that if you want to have a computationally efficient estimator in high dimensions, you can only handle vanishing amounts of noise using previous approaches. Thus raising the question, is robust estimation even possible in high dimensional settings? And our main result is that we gave the first algorithm which is both efficient and accurate in high dimensional settings. What do I mean by that? Here's a form of a theorem, sort of the most basic theorem we have in the paper. Given an epsilon corrupted set of samples from a Gaussian with unknown mean and known covariance, there exists an efficient algorithm to compute a proxy for the mean, such that we have the following guarantee. We have that the L1 distance between the true Gaussian and a Gaussian with this proxy for the mean is going to be O of epsilon times square root log 1 over epsilon. Note that this is pretty much what we were looking for, up to the square root log 1 over epsilon factor, which, the main thing is that it's dimension dependent. And also, this runs in polynomial time.
Gautam, I have a question.
Yeah.
So is this true for general distributions or is this true for normal distributions only? Because I remember from a survey from Diakonikolas that doing distribution learning in a supervised way for high dimensions, it has not solved, at least the computational part has not been solved yet. So what's the difference here between your work? Or maybe the review that I saw was from 2017 or something like that. Maybe it's old, I don't know.
It's possible. There's different settings. I think the survey you must have read is actually like, this is joint work with Ilya, so like he probably wrote about this at the starting point. There's certain cases it doesn't require the data to be Gaussian. In particular, I'll mention sort of midway or towards the end of this talk that we can also handle, say, things with just bounded second moments, which is a much weaker assumption, or things with sub-Gaussian tails.
Okay.
So it definitely doesn't require Gaussianity. There are some other settings where computation is kind of a tougher question. For example, if you want to use the information that a distribution has, like bounded fourth or eighth moments, this is like kind of weird, and there's computational issues that arise here, which I'm happy to talk about offline, though.
Okay. Yeah, because I remember in the survey, the main method that was used was interpolation. And there was a problem with kind of using this interpolation, extending the interpolation method to high dimensions.
I see. Yeah, we can chat about that later. I think there are some issues there in slightly different settings.
So Gautam, I have a question.
Yeah.
So in the theorem, the stated theorem, everything generalized when you replace the identity with like arbitrary covariance?
Not immediately, in the sense that like if you want to do unknown covariance, we have an algorithm for that, but you kind of have to estimate the covariance using more sophisticated methods, and then you can do the mean.
But the dependence, the error is still independent of the dimension.
Yes, that's sort of the crucial thing. We're trying to get no dependence on the dimension.
All right.
Thanks. These are all very good questions. This is sort of the main result. So are there any other questions before we continue? And I'll tell you a bit about the methods and give you some intuition as to what happens here. Let me mention there's also a concurrent and independent work with a similar flavor. We didn't actually know about this, but they submitted it to the same conference after we posted online. It appeared like 2 days later, where it's comparably, like qualitatively similar results. They have like a log in the dimension dependence, but yeah, essentially, I think it was really emblematic as to how these are important challenges, which the theory community sort of agreed that we should study at this time. Cool. So I'll spend the next sort of portion of the talk trying to get into some of the ideas behind this approach and why, naive methods get stuck and how we kind of get around it, giving you kind of like the one big intuition as to what to do. So let's talk about why naive methods get stuck. Here's a simple algorithm, which you might have even thought of when I introduced this problem to you at first. So let's remove all the points from the data set, which are obviously too far to be from the Gaussian, and then we take the empirical mean of the remaining points. So this is well defined, except for what does it mean to be obviously too far from the Gaussian. So we'll get a little bit more technical here. How far is too far? So in one dimension first, let's start with 1D. This is a very basic fact about a Gaussian. This is essentially saying that there's not much mass in the tails of the Gaussian. They die very quickly. And in picture form, this is kind of what I'm saying. You can see that if you go out root log 1 over epsilon standard deviations, you can see that there's very little mass contained in the tail. So this is a picture I want you to kind of have in your head. Everything's well concentrated in the Gaussian, and we'll keep this picture up at the top right for the time being. So in other words, if we truncate, that is remove any point which is sort of root log 1 over epsilon far from all the other points, then we'll have the following two guarantees. First, using this tail bound, we'll remove at most an O of epsilon fraction of the good points, and simultaneously, we'll have the guarantee that all the remaining bad points are at most O of root log 1 over epsilon away from the mean. So putting these 2 points together in the careful way, we'll say that the empirical mean of the remaining points satisfies, the robustness guarantee we wanted. So it seems like in one dimension, this algorithm, very simple algorithm, remove the far points and take the empirical mean, was very effective. It'll give you this epsilon root log 1 over epsilon answer. However, the issues come up when we move from one dimension to higher dimensions. So I'm not going to go through all the calculations again, but I switched in from one dimension to d dimensions. I switched in the appropriate concentration inequality, and skipping forward, you can see we got the square root d factor, which is exactly what we were trying to avoid. So that's not really the most satisfying thing. And let me show you via some pictures as to what really happened here qualitatively. So here's a Gaussian data set and what corruptions look like in 2 dimensions. So you can see the blue points here are the normal data points, and the red points are the corruptions. You can see that the points, either they're kind of very close to the mean, say things in the center, they're very close to the mean and they don't affect the empirical mean much, or they're very far from the mean, and then they're easy to detect. Like this one, maybe you can say, okay, this is far from everything else. This is definitely an outlier. So things seem like okay in 2 dimensions. You can do this, pick and choose, see which individual points are bad and get rid of them. However, in high dimensions, the picture looks something more like this. This is sort of a caricature of a Gaussian in high dimensions. Kind of the idea is that every point in a Gaussian lies in a very thin spherical shell. And so this is what it'll look like more in high dimensions. And here you can see that, individual points, no individual point really sticks out too much. In particular, how can you tell this point right here? I pointed this red point here. How could you tell that's an outlier or not? The answer is you can't, just by looking at it alone. Furthermore, even more troublingly, you can see that these are all sort of equidistant away from the mean. You'll see that these are all about square root d away from the mean. So every point is very far from the mean, and the contribution of a single point can be very large even in the setting. Kind of thinking about this and basically using the fact that things are indistinguishable if they lie in the spherical shell, you'll get that any method that looks for outliers individually will get stuck at this epsilon times square root d, thus picking up this root d factor, which we were trying to avoid. So the main insight and idea is rather than looking for outliers individually, you instead have to look for outliers more globally. And this will be formalized in this following slide. The following slide is like kind of the most important slide in the whole talk in the sense that it's the main idea. There's some technical version of it, but really the main idea is sort of contained right here. So the idea is the following. If the corruptions move the mean, so just to show what I mean by moving the mean, this blue X is the true mean of the data set, but you see all these red points here? You'll see that these shift the mean. There's a caricature, but they shift it up and to the right. So the idea is if the corruptions move the empirical mean, then they will also shift the covariance matrix. So recall for the time being that we assume that the covariance is equal to the identity. In fact, the fact that the empirical mean was moved will result in the empirical covariance being skewed like this. And in fact, it'll be skewed in a direction which kind of points towards the outliers. You can see sort of up and to the right that this is where most of the outliers lie, and it's sort of pointing them out with the empirical covariance. So this right here is kind of in one slide, one picture, the main core idea behind all our algorithms. One thing I'll comment is, again, I mentioned like this looks kind of very suited for the case with the identity covariance. Trust me, it can also be used to handle the unknown covariance case, but it's a more complicated picture, which I don't think I'd be able to get across in one simple slide like this. So yeah, that's the main idea. Instead of, what do I want to say? Yeah, the main idea is the fact that moving the empirical mean will move the empirical covariance. Now let's try to get a little bit more technical and sort of formalize this statement. Actually, no, I guess I left that out of this talk. But okay, so like this gives an idea. Instead of computing the main idea will be to compute the empirical covariance, and if it looks funny like this, this will be a hint that the empirical mean is wrong, and therefore it'll give us an idea of where the outliers lie. So here's what the algorithm is. It's very simple, and I'll describe it in one slide. The idea is the following. We're going to compute the empirical covariance, and we're going to subtract out the identity. Recall the identity is what we were expecting, but we're going to see how different it is from the identity. And we'll take the top eigenvalue eigenvector pair of this resulting matrix. And we'll branch at this point. First up, if the top eigenvalue of this difference is large, this kind of means that something is off. Something was, there was some error in this in the empirical covariance matrix, and therefore we should look a bit closer. So if we have a large top eigenvalue, what we're going to do is project data in the direction of the corresponding eigenvector, right? If you have a large eigenvalue, it usually means something interesting is going on in that direction. And so this is what it looks like. I projected our Gaussian data onto the top eigenvector, and you'll note that a Gaussian, when projected into any one dimension, will look kind of like a Gaussian. The thing is, I told you something interesting must be happening in this direction B. So the idea is that we want to remove points in the tail where the Gaussian data looks non-Gaussian. So I've really lied to you before. This isn't actually a Gaussian. You'll see that I made this tail a little bit heavy. I injected some outliers here, which will affect the empirical mean in this direction. So in fact, what we're going to do is chop off this tail right here and remove some of the outliers in this direction, which will give us a better estimate for the mean. So that's what happens if we had a top eigenvalue which is large. We project in that direction and sort of fix things up in this direction. Otherwise, if the top eigenvalue is small, then in fact the intuition we gave in the previous slide, the contrapositive of that statement, will say that the empirical mean is actually accurate. And in fact, we can just report the empirical mean of the data set, and that'll be a good estimate for the true mean of the data set. So this is essentially the entire algorithm. Yeah, you essentially just repeatedly do this procedure until you get to this case where the top eigenvalue is small enough. So it's a very simple algorithm, and it leads to the following theorem. Given an epsilon corrupted samples, a set of samples from a Gaussian, after at most, say, d iterations of the filter, is going to output a proxy for the mean, which has this L2 norm guarantee for the true mean. In practice, far fewer iterations are required. And from this, I'll sort of move, this was sort of the most technical part of the talk. I'll be moving here a little bit more in terms of experiments and also showing you some extensions to supervised learning. But before I continue, are there any questions about this algorithm or anything theoretical I've set up to this point?
So I have a very basic question.
Sure, yeah, go for it. Hello? Hello? I can see you moving, Amit, so. Maybe, is he having connection issues?
I think he might have thought his video was off and he was muted, and now he just muted himself and turned his video off.
Okay.
Okay, so yeah,
oh,
I had like a minor, I had a minor connection issues.
Okay, sure.
So I'm not an expert in this, but how is it like different than like taking the data and doing a PCA?
The thing is that PCA will kind of give you, it is essentially like doing a PCA to find the important directions and then see if something looks wrong in them. Yeah, in fact, it can be seen as a type of PCA.
Okay, I see.
But like doing it the appropriate way and very carefully and like doing the analysis is sort of non-trivial.
Right, okay. Thanks.
Any other questions?
I've got a pretty basic question as well.
Sure.
So in this case, you said like the points were sort of in one direction and like one side of the tail. So you were able to like truncate on like one side of the tail after projection and then take the empirical mean, but like you don't necessarily know how exactly the corruptions are happening, right? Even in that direction. So how do you deal with the general case?
Sure, kind of. Okay, so it's not necessarily all on one side, actually. I simplified it a bit. In fact, it could be corruptions on both sides, but the idea is we're just going to chop off the tails at like sort of absolute value to find whichever points are bad. And kind of the way that, okay, let me put it this way. If the points were actually near the mean, they weren't in the tails, then they wouldn't affect the empirical mean. So somehow using the fact that something went wrong and the fact that the variance is large in a direction, that implies that the data is in the tails, which is what caused the issue.
Okay, that makes sense. Thanks.
Cool. Yeah, any other questions?
I actually have a question. So, but in the picture that you showed us, like, in a sense, if you go back to the previous picture, right? Like none of the points, like, yeah, that one. So
Yep.
yeah, with the ellipse, right? Like in a sense, like the problem that you have here is not that, like there is any outliers, right? Like you're not chopping off stuff that's outlier because you don't have many outliers. The problem here is really that all of your points are concentrated on one side. So like, how is this picture seems different than the other one that you were explaining, right? Because here
I guess
you're saying,
yeah, it's different because it's like it's trying to do a high dimensional version of the thing, perhaps poorly, but like the sort of appropriate actual picture of what this looks like in high dimensions would look kind of similar. But if you do the projection in one direction, it will indeed have this sort of issue where like one tail is actually heavy. It's a sort of this needle in a haystack type phenomenon that you don't immediately know which direction that is, but doing some spectral analysis of it will sort of indicate where that direction is.
I see. So it will look skewed in the eigenvalue, right? In the proper eigenvector. Okay.
The spectral information, the eigenvalues and the eigenvectors will really reveal where the directions are.
Okay. Thank you.
Cool. So I'll move from here to a little bit more experimental for a few slides, and then I'll move on to like an application, sort of a neat connection with how we might do robust learning in a data poison setting. So okay, unsupervised learning, first of all. This is from, with the same group of co-authors. This was in a paper in ICML the following year. So essentially what we're trying to investigate is, can we actually use this algorithm? The first thing was just purely theory, but then we went on from there to do more experimental results, as well as remove some of the restrictions. Let me mention, I don't have slides on this here, but I'll just say that, again, we assume that the data was Gaussian, but one of the main things of this paper that we do here is try to relax that assumption, because real world data often isn't Gaussian. Often you have weaker knowledge of the distribution. Maybe it only has bounded second moments. So we came up with another version of the same algorithm, sort of a modification of the algorithm, which handles distributions with bounded second moments and other sort of settings like this. But what I'm going to be focusing on the next few slides is telling you about some of the experiments and showing you that it really works. So we had the setup where we have, say, 90% Gaussian data, 10% adversarial noise. We looked at, say, an isotropic Gaussian, that is a Gaussian with identity covariance, and we want to estimate the mean and covariance. And also, say, a skewed Gaussian where we want to estimate the covariance. And how well do we do in these cases? So here's some synthetic data experiments with unknown mean. So you can see, let me try to explain this to you. So each of these plots has the dimension on the x-axis, and the y-axis is the excess error, which is going to be like kind of, yeah, let's just say, it's the L2 error of the estimate. So what we did here was we plotted a number of different approaches. So the black line is the filtering approach, which is our approach. LRV mean is the result that I mentioned, which was concurrent by Lyra and Vimpala. And the others are sort of more classical approaches, which were actually computationally efficient. We obviously couldn't run the not efficient ones, but they're very basic. Some of them are basic things like geometric median or sample mean, pruning, etc. So okay, let's compare them. You can see in the left plot, these two contemporary methods have error close to 0, but everything else has much larger error, which even increases with dimension. And if we zoom in on just compare our method versus LRV's method, you'll see that our error is significantly lower, and it doesn't really increase as you increase the dimension, as sort of the theory predicts. And the code for this I'll mention is online. So that's the sort of simplest case, but this also continues for unknown covariance. So here are different approaches for trying to estimate the covariance. So again, we can compare our method with the Lyra-Vimpala method, as well as a few other options, sample covariance or like a pruning method. And you can see in like reasonable numbers of dimensions, 20 to 100 dimensions, we still have error which looks kind of like 0. Everything else is increasing. And this is for the identity covariance case. And in the skewed case, it was even more dramatic in the sense that our error looks like it remains at 0. LRV's is significantly non-zero. Ours is not literally 0. It's just the fact that you can't display it on the same scale. And in fact, you might be wondering where these two baselines went. Well, they went way, way up. They're like in hundreds or thousands. We couldn't even meaningfully represent them on the same scale. So this kind of shows that, what is the takeaway? What do I want you to get out of this picture on the right and the absence of these two? The fact is that classical methods, when you have a sort of skewed data set, seem to give you something which is not at all usable. Whereas our algorithms might give you the first idea of how to really do something meaningful in these settings. So that's all fun and games for synthetic data analysis. Let me show you one sort of more a semi-synthetic data experiment, which I thought was really cool. And this is the kind of type of thing you could see being used in practice in terms of exploratory data analysis. Where essentially, imagine you're a data scientist and you want to sort of see what interesting structure exists in our data and what can we do with it. So let me mention that a sort of key primitive here is robust PCA. This you might know of from like previous, there's well-known works on robust PCA, but we're doing something slightly different. I won't get too much into like the differences between the two settings here, but like essentially what PCA is, it's essentially trying to find the directions of maximum variance in a data set. So, you have this one, and the long direction is kind of what you want to discover. But imagine in a robust setting, you have data points which are adversarially placed, which can misdirect your algorithm. So the goal is, imagine we're in a setting like this, and we want to discover this long direction rather than this direction due to these outliers. And can we do stuff there? And like I said, it'll be sort of incomparable with the robust PCA setting of Condes et al. So I'm not going to get too much more into that. But in order to sort of demonstrate this method, I'm going to bring back a classic study from November et al., which appeared in Nature in 2008, titled Genes Mirror Geography in Europe. Let me explain their experimental setup. They were a bunch of, they took a sort of high-dimensional genome data set from a number of individuals in Europe, sort of a gene expression data set, and they colored each data point according to the individual's country of origin. For example, if they were from Spain, they would color the point blue. From Great Britain, they would color it pink, and so on. They then did the following experiment. This was the following scientific analysis. They took this data set, they computed the top two principal components, that is, they computed the top two principal components. They projected the data in those top two principal component directions and plotted it in the plane. And the image you can see is the one on the left. You'll notice that this experiment essentially this map, the picture on the left, very closely resembles the picture on the right. To sort of explain this experiment in case it went kind of fast or you didn't follow it, let me sort of rephrase it and say that the idea is that they found that the two directions in sort of the genome space, which explain most of the variance, correspond somehow to the two dimensions in geographical space, latitude and longitude. So this was kind of a big deal, and people were very impressed by this and thought it was like, it was pretty neat. But there's something I didn't tell you here. And the fact is that before they did this experiment, they manually curated the data set by hand to remove outliers. In particular, you can imagine an immigrant who travels to Spain would have a very different genome. And therefore, they removed people like this in order to make the results like look better. So this seems like exactly the type of setting which we would want to be able to address. Can we find some underlying structure even when the data set might be corrupted in some way like this? So we addressed this by looking at a sort of semi-synthetic case where we introduced our own outliers, and we found the following. If you try to use the same experiment, well, Europe is destroyed. You can see the image here, running the exact same running the exact same experiment, taking the top two principal components, you now lose all the structure that was present in the data set before. And now it's like a garbled mess. And using some of the other approaches which you might consider, say the ransack approach, which is a classic approach in statistics and data science, also doesn't help. You know, other approaches for robust PCA in the other sense that I mentioned also don't work. But on the other hand, our method manages to pretty reliably return the same structure that was present in the data. You'll notice this is on the left is the original data set before any sort of outliers were added. The middle one is what happens if you run our algorithms after corruptions are added. So you'll notice that they look almost the same. There's some differences. For example, you can see these 4 points here, which correspond to individuals from Turkey, were removed. But that's because they're kind of already far out, so it's not clear whether they were outliers in the first place. But yeah, I think I was pretty excited by this experiment, and shows that perhaps in some cases our tools could be used for exploratory data analysis, discovering structure where it might have previously been obfuscated. Cool. I'll move on from here, and if there's no questions, I'll move on from here to another setting, which is that of supervised learning, just showing how some of these tools can even be useful in the supervised learning setting. Yep, question?
I have a question, yeah. So in
Cool.
your picture, so would you think, like, I mean, often I think in machine learning, like when people are talking in practice, I mean, I don't know much, I mean, but that's what I hear, is that, I mean, outliers are important to understand where they come from, right? So do you think that also, like, your explanation could explain that most of the immigrants are coming from a certain place? Because in a sense, through your algorithm, they would have to have a similar genetic material to shift the mean, right?
Yeah.
Can
exactly.
you guys explain this as well, or?
I guess what this algorithm will do is, like, notice how it like removes some points, and it'll like identify, basically it'll label points as outliers, whatever that means. So from there you can do additional analysis, like try to figure out, okay, is there additional structure in these outliers? Are they all sort of like in one little cluster here? Is there something they have in common? Are there little clusters? So then I think at that point, once you identify the outliers, then it's sort of domain dependent what is really going on there. You can sort of, but you can do further analysis on it.
Okay, but essentially what you're saying is that, like, the reason why you can remove the outliers is because they're concentrated, right? Because, well, if they didn't affect your mean, like, you could potentially have said, like, okay, they don't change anything, right?
Right, yeah, exactly.
Okay.
Cool.
So, sorry, I have a question. Maybe I missed something, but you said that they had data and they hand removed outliers.
Yeah, they manually curated it.
So is there any hope of, like, actually using your algorithm to see what happens if you don't curate the data first?
I would like to do that. The challenge is the fact that some of these biological data sets are locked behind, not paywalls, but locked behind, walls, so that, the average people can't get hold of people's genetic data. So I think at some point we filed a request for, like, the genetic data set through when I was still at MIT. And I don't know, maybe it didn't work out. So, like, this is the best experiment we could kind of do with the data that we found publicly available. But
I see. Okay.
I am interested in doing analysis in other settings where Yeah, if there's other one of the, let me just say, like, my pitch is that I currently I'm looking for more scientific settings where perhaps this could actually give us new scientific findings. So if anyone knows settings, please chat with me either after or later on. But yeah, good, excellent, very insightful question. Yes.
Yeah, yeah, sorry, yeah, exactly. So just to summarize the Bryce's question, which is really interesting. So you guys ran the experiment on their curated data. Is that right?
Yeah, like I said, it was semi-synthetic, which means that there's some real data, which is the data that they had, but we introduced our own outliers as well to see what would happen.
Oh, I see. And you did like, and all of these other experiments that you said as well were also on synthetic data, on the same synthetic data.
So the previous sets of experiments, these experiments were on fully synthetic data.
No, sorry, the ones that broke Europe.
Yeah, exactly. All of these ones that broke Europe were on semi-synthetic settings.
Okay. Thank you.
Cool. All right, I'll move on to the last little vignette, which focuses more on supervised learning. This is a somewhat more recent paper, which we titled Sever. It's with a similar cast of characters. This one includes Jacob Steinhardt. But yeah, so let's see if we can go beyond robust statistics. Can we optimize more complicated objectives with corruptions? Before we were just sort of looking at mean and covariance estimation, can we do something more? And we're going to look at sort of robust stochastic optimization. That is kind of a formalization of, essentially I'm saying, can we do supervised learning, let's say. More formally, we're going to have a distribution D, which is a distribution over the input of x, y pairs, where x are the data points and y are the labels. There's some loss function where it takes in a point, its label, as well as a sort of a parameter vector w. And the goal is the following. Given an epsilon corrupted set of samples from whatever data distribution, we want to find a parameter vector w, which minimizes the expected loss. So if this sounds a little bit like a bit weird or unfamiliar, well, this is like, there's nothing I'm really doing too complicated here. If you substitute in the loss function y minus the inner product of w and x and square that, that's essentially just a linear regression. This also it can encode SVMs and more generally generalized linear models. So essentially we're trying to solve these types of problems. Let me also note that this can also be, say, neural networks if you'd like, just having the appropriate loss function for that. We have slightly different guarantees for that sort of setting, but yeah. The goal is essentially to try to minimize this where an epsilon corrupted set is going to be changed as before. And we're going to let the corruptions change both the data points as well as their labels, really arbitrary changes. So, okay, how do you solve this type of problem classically? Well, anyone who's taken the basic class in ML will know that you can solve this in the non-robust setting using gradient descent. Essentially, we'll have update steps like this. You'll see that W is our parameter vector, and we make steps, which this is the sort of learning rate, and we take the empirical mean of the gradients at each of the data points. So this is just gradient descent stats ML 101, let's say. And the goal is that essentially we want to follow the negative of the gradient of the function, but in place of this true negative gradient of the function, we take the empirical gradient in the vanilla setting. So that's kind of what works in the non-robust setting. But what if some of the xi, yi pairs are corrupted? How do we robustly estimate this gradient of the function? We can't just take the empirical mean of the gradients. And in fact, if you've been paying attention in the sort of first 75% of the talk, the idea is instead of using just the naive empirical mean estimate here, we're going to use some of the tools that we've constructed. So in particular, we're going to be able to robustly estimate this function using a modified form of gradient descent. That is, this is the exact same type of update rule as before. We're going to take the previous gradient and make a step based on some learning rate times g of t, where this time g of t is a robust estimate of the true gradient of the function. And this will be obtained via the robust estimators that I've mentioned from the first part of this talk. Like I said, while for the first part I focused on Gaussian cases, in fact, bounded moments of x of the data points often suffice to bound moments of the gradient of the loss function as well. And this will be kind of all we really need. I'll mention another simultaneous work by Prasad et al., which also does robustify gradient descent to solve this type of problem.
So Gautam, what problem are you solving with this method? Is it some kind of robust objective function?
The objective function is just going to be, say, linear regression or like the SVM objective function, hinge loss, stuff like that.
Okay.
Yeah, it's going to be the standard loss function, except the difference is the fact that some fraction of your data set might be corrupted.
Yeah, I'm asking this because, I mean, you're not essentially minimizing the actual empirical mean anymore, right? You're doing something else. Or...
Correct, yeah, exactly. It's not going to be the empirical mean of the gradients. It's now going to be like a robustified mean of the gradients.
Okay.
Cool. So essentially, our main theorem is something like the following. Essentially, if we have this technical condition which says that the covariance of the gradients is bounded by sigma times the identity, then Sever, which is our algorithm, will locate a sigma times root epsilon approximate critical point. So notice that this is just like an approximate critical point. In particular, we don't say anything about, like, some salient features of this is that this does not rely on convexity or anything like that, strong convexity. Those will result in better algorithms which find global minima. But really, this sort of robustifies any sort of training algorithm, even say neural networks and stuff like that. It'll just find approximate critical points. And this is based on a second moment filter idea rather than a Gaussian filter, like I mentioned. But right. Furthermore, if we have the fact that the loss function is convex, then we can approximate the optimal parameters. That is, we can get some sort of parameter proxy, which will result in something which is close to the true parameters, the true loss function. And then we also have additional specific sample complexity results for linear regression, SVMs, logistic regression, and more. So that's for theory. Let's see in terms of like, there's additional tweaks we have to do in order to make this practical. Running out of time, so we'll wrap this up quickly. In particular, the filter is kind of relatively slow. I'll just mention, I'll just say really quick, like rather than doing like a robustified gradient descent at each step, essentially we do a non-robust gradient descent to optimality, and then we run the filter once, rather than this will be much faster in practice, and it essentially has the same theoretical guarantees and be much faster in practice. But yeah, let's just, I'll show you some experiments and then conclude. Essentially we do, yeah, I'll skip over the setup. It's basically, I'll just show them to you here. So first we had some ridge regression experiments, basically linear regression with some sort of regularization, and we compare our results with several others. Let me explain the graphs to you. These are different from how they were before. This time, the x-axis is the corruption, the outlier fraction. So this goes from 0% outliers to 10% outliers. And the y-axis is the test error. So you can see that we compare our method, Sever, which is the black line, with first of all, the uncorrupted, like how good is the error if you didn't have any outliers at all, and a bunch of similar, simple baselines in terms of removing points. For example, removing the points with large L2. Was there a question?
No, I think it was just someone unmuting.
Okay. Anyway, so yeah, we compare with a number of baselines, such as removing points which look bad in different ways. And you can see for regression on synthetic data, our error is essentially close enough to 0. Actually, yeah, in the synthetic data experiment, we had a ground truth. So like we actually, I think, recover the ground truth essentially up to small error, whereas other approaches don't work. On a real-world data set, a drug discovery data set, we managed to get sort of comparable to uncorrupted. And on that same data set, even if we try to cherry pick, the results which make us look the worst, like the very worst case, you can see we're still competitive with even the best of the other baselines. Yeah, and the code is online for this as well. I'll mention sort of similar results. I won't get too much into it. We also did SVMs on, say, synthetic data, as well as SVMs on the classic Enron data set, which many of you are familiar with, I'm sure. But this is like a spam classification data set. And you can see that we're sort of still quite good. Even when we cherry pick attacks against our own method, we find that still none of the other methods can outperform us, even in that setting. One thing I'll mention here is I think this is actually pretty interesting to see. Notice the outlier fraction is so small here. It's just at 3% outliers, you can change the test accuracy by so much, which I think is a very interesting phenomenon. Yeah, this is just sort of a bit aside, though, not relevant to the rest of it. Yeah, and with that, I'll sort of mention some conclusions. We provided some methods for robust estimation, which are applicable in many settings. We gave the first computationally efficient algorithms for this setting. They're sample efficient, accurate in high dimensions, and interestingly, I think promisingly, they're realizable in the sense we could implement it and they actually seem to give promising results. So, but there's still a lot to explore. I'm currently looking for the big picture question in this area, in particular whether we can do like real science using these type of methods. And so I'm very excited, hopefully, to like talk with other folks. Let me mention also, give a shout out. I think I saw Shubhankar here earlier. One interesting direction which I've been looking in more recently, these are kind of adapted from old slides, but are wondering whether this can be doable in a differentially private setting under, you know, if the data is sensitive as well, which is very important for, say, medical applications. So Shubhankar Mohapatra, who's a master's student here at Waterloo, has been like spearheading a project on that in joint work with myself, Shiha, who's also a colleague, and Om Takar. But yeah, there's still a lot more to explore, like I said, and I'm hopeful to find more applications. So if you know of any, please talk to me. I'm happy to take questions and hang out for anyone who wants to hang out.
So I have two questions. The first one, what's the sample complexity of?
Yeah, good question. So like the sample complexity of all these is like, if you ignore log factors, basically the same as the original sample complexity. Yeah, it's like, for example, if you want to estimate the mean of a d-dimensional distribution, this is order d over epsilon squared. And if you want to estimate the covariance, that's d squared over epsilon squared.
Okay, and the other thing, sometimes you know stuff about like the corruptions, like you know some things about this distribution. Did you guys consider like, I don't know, some models of noise and to get like a better results?
It's a good question. Yeah, like, so one thing is I'll say that our method is like this is a very tough corruption model. It's kind of the most adversarial corruption model you can imagine. So in particular, it gives results for pretty much any other setting. But yeah, I don't really know too much what you would actually gain by switching to another setting, in the sense like we have fine sample complexity, the running time, further improvements by, you know, Jerry and Sam Hopkins have improved it down to like near linear time. Yeah, I'm not really sure what you would gain, but it's a good question. Yeah.
Okay, thank you.
Yeah.
Okay, so before we open up for more questions, let me just try this. Let me try to unmute everyone and we can clap, and then I mute everybody. And then, okay. All right, we can clap now. Everyone's unmuted.
Oh, thanks. This was actually surprising. I've always been afraid to try this sort of thing because I worry it's going to be really awkward, but that was actually not bad.
Okay, good. So then, everybody can mute yourselves now. Yeah, we can keep asking questions. If you want to leave, you're free to leave as well. Let me